So today we are going to take up one more new technique, that is centrifugation. So in centrifugation, I'm going to tell you different types of centrifugation. So there are different classifications based on the instrument, based on the uses. So we'll see all those types. Then uses of centrifugation and how centrifugation is one of the most important technique used in most of the labs. So all those points we'll see. So coming on to the first slide, I think you all should know that this centrifugation was first discovered by Swedberg. I think this name is known to all of us. So we all know the Swedberg constant, right? So Swedberg was a gentleman who first discovered different types of centrifugation. So he was working with the colloid or the colloid solution, or that time people they used to call it as salts. So he was working with salts, and then he wanted to separate these salts into different constituents. And in that fluke, he discovered this particular centrifugation method. And he was the gentleman who first discovered centrifugation with a photographic facility. So he wanted to photograph the separation of different salts into the mixture. So he discovered analytical centrifuge instrument where he put this salt, and then he captured the image of that separation based on the centrifugal force. So Swedberg, along with his students, so they are considered as the discoverer of this particular technique, that is centrifugation. So now, if we have to define centrifugation, it's centrifugation is basically a technique, as I have written here on the slide also, which is used to separate a particle based on the specific physical characteristic of the particle, like size of the particle, shape of the particle, density of the particle, even the medium which we are using to separate the particle, that is the viscosity of the medium, and the rotor speed or the type of rotor which we are using. So all these variables clubbed together affect the centrifugation of the particle. And centrifugation is also defined based on the device which you are going to use to separate a constituent or a material from a solution using different type of rotors. So particle may be anything. Maybe it is a biological, maybe it is something else like cell or subcellular organelle or large molecule. So we all know the term centrifugation. This centri means center, fugation means separation. So it is the separation based on a particular basic theory, that is the force or the centrifugal force. That's why the term has been coined as centrifugation. Here, particles basically settle down at the bottom because of our gravitational force. We know that we all exert a gravitational force on our head. So this particle, especially in case of centrifugation, it settles down at the bottom due to gravity, and all this gravitational force, you know, is denoted by G. So this centrifugation increases with the rate of sedimentation. So we are going to increase the rate of sedimentation by steaming the sample. So in subsequent slide, I'll tell you what is this rate of sedimentation. So there is one term which we should know. So centrifugation is directly correlated with the rate of sedimentation, and then settlement of any particle in the solution is directly correlated with the rate of sedimentation. So that we'll see in subsequent slides. Regarding basic principles, so we all know that there is two force when you spin something. So basically it exerts two different types of force. One force is the
sir. Excuse me, sir. Sir, it is showing only the first slide. The slides are not changing.
It's not.
Yes, sir. It is only fixed in the first slide.
Okay, let me.
Yes, sir.
Now it's changing?
Yes, sir.
Yes, sir.
Okay. Now it's changing?
Yes, sir.
Okay. Can you see this slide, basic principle?
Yes.
Yes, sir. Yes, sir.
Sir.
Shall I?
Yes, sir.
Okay, so I was telling that we all know that when you spin something, so it exerts two different type of forces. One is called as inward force. Basically, that is your centripetal force. Even you can see, you can visualize in the diagram that there are two arrows. One arrow is towards the inward, towards the center. That is basically the force which is called as centripetal force. There is another force which is exerted outside, out from the center. That is called basically called as centrifugal force. So if you see the sentence I have written, it involves the use of, it means centrifugation, basically involves the use of centrifugal force for the sedimentation of heterogeneous mixture with a centrifuge. So basically this centrifugal force is the basic principle behind the settlement of all these particles which is present in your mixture when you spin that at a high speed. So there is another term which is related to this. It is called as relative centrifugal force. Relative centrifugal force is basically the force which acts on that sample during centrifugation. RCF, it is also denoted as RCF. So relative centrifugal force is the force which acts on the particle when you spin it at a very high speed. It is also expressed as a multiple of the Earth's gravitational field, which is denoted by small g. If you see the next sentence where I have written a correlation that the rate of sedimentation is directly proportional to the applied centrifugal field. Rate of sedimentation is directly proportional to RCF. RCF is relative centrifugal force, and the equation which expresses this RCF, so it has been derived from different calculations which I have not accounted here. So if you see RCF equal to 1.18 into 10 to the power minus 5, and there is the RPM square, revolution per minute square, and then there is a small r, and the bracket is closed, G unit. So G is the unit in which we express the relative centrifugal force. 1.118 into 10 to the power minus 5 is a factor, and then RPM is revolution per minute. So this is the equation which is basically used to convert RPM into RCF and RCF into RPM. I think many of you have used centrifugation, and when you use that centrifugation, so most of the time RPM and RCF will be written in your protocol, either RPM or RCF or both. So this is the equation through which you can convert your RPM into RCF and RCF into RPM. The another thing which comes from this equation is that relative centrifugal force is directly proportional to the radius of the particle which you are going to use, the radius of the rotor which you are going to use. So these two things we should know. Many a times people, they used to ask this correlation that RCF is directly proportional to or RCF is inversely proportional to. So you should know that RCF is directly proportional to the RPM. It is directly proportional to the radius of the motor and the radius of the particle which you are going to separate. So coming on to another term which is very popularly used in centrifugation, that is sedimentation. So I think in our routine day-to-day activity also, many a times we are using this word sedimentation, means settlement. So the rate of sedimentation, which is basically used in centrifugation, so rate of sedimentation is defined by an equation which I have written here. If you see, rate of sedimentation, which is denoted as R, is equal to 2. Then you have a term RP. RP stands for radius of the particle which you are going to separate. Let me repeat once. I told R. Yeah, RP here stands for radius of the particle which you are going to separate.
Sir, it's in the
So the
previous
slide is
slide.
not visible again.
Yes? Can you
The
see this?
slide is still fixed, sir.
It's not coming. Now?
Now it is
Now
okay.
it's okay, sir.
Okay, so maybe I don't know. So now it's visible?
Yes, sir.
Yes, sir.
Okay. Yeah. So about sedimentation, and I told that even in our day-to-day activity also. So we are using this term, which basically means, just 1 minute. Yeah, which basically means that we are going to settle something. So in case of centrifugation, the rate of sedimentation is represented by an equation which I have written here. If you see rate of sedimentation, which is basically denoted by small r, so it is equal to 2 rp square. Here rp is radius of the particle which you are going to separate. So in other words, we can also call that rate of sedimentation is directly proportional to the radius of the particle which we are going to separate. So this is one of the correlation which we should know. Then next, if you see, there is a bracket where I have written rho p minus rho m. This rho p is basically density of the particle. It is the density of the particle which we are going to separate. Rho m is density of the medium which you are going to use. Rho m is the density of the medium and rho p is the density of the particle, and whole these two constitute difference in density between the particle and the medium which you are going to use. So the another equation which I can derive from this is rate of sedimentation is directly proportional to the difference in density of the particle and the medium. It means the difference or the density between the particle and medium is one variable which influences the rate of sedimentation. Then third factor is omega square r. So this is basically the angular velocity which we are going to use. So rate of sedimentation is directly proportional to the angular velocity. Then if you see the denominator, so here I have written 9, which is a factor, and then there is a eta. So rate of sedimentation is directly proportional to the particle of the medium, particle of, it is directly proportional to the radius of the particle. It is directly proportional to difference in the density between the particle and medium. And then denominator I have written 9 eta f by f0. So here f stands for frictional coefficient, and fo it stands for theoretical frictional coefficient, which you are going to calculate, theoretical frictional coefficient. So rate of sedimentation is inversely proportional to the frictional coefficient or ratio of frictional coefficient to the theoretical frictional coefficient of the medium, and it is inversely proportional to the viscosity of the medium also. So altogether 5 different derivations we have derived from this particular equation, and anywhere you can expect such type of questions where people, they will expect that you should know that rate of sedimentation is inversely proportional to, rate of sedimentation is directly proportional to, and what these terms stand for. So again, to repeat this, I told rate of sedimentation is directly proportional to the radius of the particle. It is directly proportional to the difference between the particle and the medium, difference in density between the particle and medium. It is directly proportional to the angular velocity. It is inversely proportional to the viscosity. It is inversely proportional to the frictional coefficient of that particular medium. So these are some of the derivations which easily we can make out from this particular equation. So if we have to define this sedimentation coefficient, which is one term very popularly used in centrifugation, so sedimentation coefficient is defined as the ratio of sedimentation rate to the centrifugal field which you are going to provide. Let me repeat once. I told sedimentation coefficient, which is very popularly used in centrifugation. It is basically the ratio of sedimentation rate, which we have seen in earlier slides, and the centrifugal field which you are going to provide. It is also denoted as S, and the equation is S equal to V by omega square R. So 1 Svedberg unit or the sedimentation coefficient unit is equal to 10 to the power minus 13 seconds. We are not going into the derivation of this equation, but we should know that 1 Swedberg unit is equivalent to 10 to the power minus 13 seconds. There are few statements which are correlated with the Swedberg unit, and we should know. A Swedberg unit is basically a measure of flow of how quickly a particle settles down during centrifugation. So when you are doing centrifugation, how fast a particle will settle down, that is denoted in terms of a Swedberg unit. So if the size of the particle is large, so it will have a greater S value. So S is the notation in which we use to denote this Swedberg. So heavier and more compact particle will have a large Swedberg number or will quickly sediment. So sedimentation coefficient is also denoted denoted by the function of a particle molecular weight, volume, and shape. So it signifies all these three variables other than the rate of sedimentation. So Swedberg unit is very commonly used, and those I think who might be knowing about the discovery of ribosome, their structural classification, so they might be knowing that all those small units of ribosome is denoted by Swedberg unit only. So sedimentation coefficient is a function of particle molecular weight, volume, and shape that we should know. And 1 Swedberg unit is equivalent to 10 power minus 13 seconds. So these two are very important points which one should know. If somebody asks you what is sedimentation coefficient, we should be very generous to tell that it is the ratio of sedimentation rate to the centrifugal field which we are going to provide. So now when you talk of centrifugation, there are different classifications. So the first and the most old classification is based on the amount or the volume of sample we are going to use and based on the uses. So based on these different parameters, centrifugation has been classified into two different types. One is called as preparative centrifugation and other is called as analytical centrifugation. Here I have listed some of the differences between preparative centrifugation and analytical centrifugation. If you see the first point, so it says preparative centrifugation is a high velocity centrifuge used in the separation of small submicroscopic particles. On the contrary, if you see the analytical centrifugation, it is a high velocity centrifuge used in the analytical process which we are doing in our lab. So preparative, if you see the third point, so it is used in pelleting small materials. So here there is no scope that you can use large volume of samples. Whereas if you see the analytical, so it is used to determine the mass, shape of macromolecules, maybe the protein or the rate of sedimentation of the molecule. And here speed is very high as compared to the preparative part. If you see the third point, a large sample size can be processed in case of preparative, whereas in case of analytical, so you can use a small sample volume, maybe less than 1 ml to process. So sample volume is one of the important criteria for the classification of preparative and analytical other than the uses or the purpose. So in case of preparative, large sample volume can be used, whereas in case of analytical, only small sample volume can be used. In case of preparative, so even we can use directly extracted sample or the crude extract also can be used in case of preparative, whereas in case of analytical, most of the time we require a purified sample or the extract which we have prepared should be purified before being used in the analytical centrifugation. Next, in case of preparative, no hard and fast rule that we need to have a specific temperature, we need to have a specific parameters to use preparative centrifugation, whereas in case of analytical, so different parameters are specified and you have to follow that in order to go for analytical centrifugation. In case of preparative, it is very robust, rough, and easily you can run, but then there is no facility for actual or real-time observation or visualization of the centrifugation process. Whereas in case of analytical, on real-time basis or actual basis, you can visualize the separation of the particles and then some of the reactions where we need to observe the change in the particle pelleting or other variables that easily you can visualize in case of analytical. So in case of preparative, other small differences that no cooling arrangement or the facility in the instrument is not advanced one as compared to that of analytical, where we have different sensors and easily you can monitor different parameters like temperature, like scattering of light, etc., etc. So these are some of the differences between the preparative and the analytical centrifugation. So there is another, if you classify these two, preparative centrifugation and analytical centrifugation, so we have different types of preparative as well as analytical centrifugation. So in case of preparative, if you see, we have three different types, which is very popular. First is differential centrifugation. As the term suggests, differential means different. So centrifugation, so there is a difference in the sedimentation rate of the particle, and that's why you can use this such type of centrifugation for a particle of different size, shape, and density. That's why the term differential. The another one is density gradient centrifugation. So density gradient centrifugation has further been classified into two different types. One is called as rate zonal centrifugation. Other is isopynic. Iso means equal, pynic, equal density centrifugation. So density gradient centrifugation has been classified into two different types. One is rate zonal centrifugation, which is basically time dependent. Other is isopynic or equal density centrifugation, which is rate independent or time independent. The third classification is centrifugation illustration. So this is basically used by the industry people. So they want to have exhaustive product out of this centrifugation. So they have a continuous system where this centrifugation will go on happening, and then they will extract the product out of that. That's why the term centrifugation illustration. So let me repeat once. I told as the centrifugation has broadly been classified into two different types. So we have different advancement in this, and these two types have further been sub-classified. For example, preparative centrifugation has been further classified into three different types. First is differential centrifugation, and as the name suggests, differential means different. So difference in terms of size, shape, and density of the particle. Another is density gradient centrifugation, and further I told this density gradient centrifugation classified in one is rate centrifugation, basically a time dependent centrifugation, and you can
Excuse me, sir.
yes.
Your voice is breaking, sir.
Actually, if you are, please mute your mic, so I think it will be. So even I am getting some sound from your side. Now, is it audible?
Yes, sir.
Shall I continue?
Yes, sir.
And can you visualize the slide?
Yes, sir. Type of centrifugation.
Yeah. So I was telling type of centrifugation, and so as it has been classified into two different types. So we are discussing about the preparative centrifugation, and again I told preparative centrifugation has been further classified into three different types. One is differential centrifugation, and as the term suggests, differential means difference in the size, shape, and density of the particle. It means we are going to separate, or we are going to centrifuge the particle based on the difference in size, shape, and density. Other is your density gradient centrifugation, and I told this density gradient centrifugation has further been classified into two different types. One is rate zonal centrifugation, and I told that this rate zonal centrifugation is time dependent. Means when you go on increase in the time of centrifugation, so all your particle will settle down at the bottom of your centrifuge tube, or maybe at the wall of your centrifuge tube. Another is isopynic centrifugation. Iso means equal, pynic means equal density centrifugation, which is basically a time independent. When you increase the duration of centrifugation, it hardly affects the separation of the particle, because particle will be separated based on the bion density, and it will just localize itself in a layer at different locations based on the equal density feature, or based on the bion density. So even if you centrifuge for 10 hours, 12 hours, 2 days, 5 days, it hardly affects the location or the space of that particular particle, because it will form a layer at a particular space based on its Bion density. So that is called as isopynic centrifugation. Third is centrifugation illitration. I told this company, industry people, they are using such type of centrifugation where continuously they need to separate the centrifuge product out of the mixture. So that is a continuous process. That's why the term centrifugation illitration. So coming on to the first, that is differential centrifugation. As I told earlier, difference, it is based on the difference in the sedimentation rate of the particles of different size, shape, and density. So such type of centrifugation can be used for separation of particles having difference in the size, shape, and density. And particles are separated in fractions by applying different centrifugal fields. So by applying different centrifugal fields, so easily you can separate different fractions of that particular solution having a specific particle. And you can use this for recentrifugation also. So once you centrifuge, you separate a specific particle, then again you go for another centrifugation. Again, you separate a specific particle. So based on the difference in the size, shape, and density of the particle, and based on the difference in the centrifugal field, easily you can separate different fractions of particle which is present in your solution. So this differential centrifugation is very common in most of the labs. Coming on to the another, as I told, density gradient centrifugation. This is very important. So in case of density gradient centrifugation, I told we have two different types of density gradient centrifugation. One is called as rate zonal, other is called as isopynic. So at the bottom, if you see left hand side, so this is basically a rate zonal centrifugation where with the increase in the centrifugation time, you see that particles will slowly go and settle at the bottom of the centrifuge tube, and ultimately it will form the pellet. If you see the isopynic equal density centrifugation, where Bion density of the particle is one of the basis for the separation. So here you have a mixture of particles, and when you centrifuge it, so based on the Bion density of these particles, it will form a different layers. And this is irrespective of time. It means even if you increase the duration of centrifugation, it hardly affects the location of these particular or the layer of these particular particles, because the basic or the basis for this separation is the Bion density of the particle, whereas here the basis is difference in the shape, size, and density of the particle, as well as the viscosity of the media. And it is because of this reason that when you go on increasing the centrifugation time, so these particles will settle down at the bottom. So these are some of the differences which we should know between the rate zonal and the isopynic centrifugation. So the first is the particle nature. So in case of rate zonal, so basically we target the particle having difference in the shape, size, and density for the separation using rate zonal centrifugation. Whereas in case of isopynic, so Bion density of the particle is the basic through which we separate. Effect of time. So in case of rate zonal, as I told earlier, it is time dependent. So with the increase in time, the pelleting will go on increasing, and it will go on becoming more crust, more layering, more hardy. Whereas in case of isopynic, it is time independent. So duration or the length of duration of centrifugation hardly affects the outcome. Medium. So in case of rate zonal, it is depend on the density and the viscosity of the medium. Whereas in case of isopynic, it depends on the density of the medium which you are going to use, because that provides the specific area for the Bion density based separation of the particles. Coming on the pellet formation, so in case of rate zonal, so easily you can expect pellet to be formed, whereas in case of isopynic, it is the layer of the particle which is formed rather than the pellet. Regarding method, so as I told, in case of rate zonal, it basically depends on the applied centrifugal field, whereas in case of isopynic, it is the equilibrium-based method which applied here. Regarding uses, so rate journal, as I told, is frequently used in our lab for day-to-day routine work, whereas in case of isopynic, so we are using this for the separation of high-quality nucleic acid or protein. So in that case, we are using isopynic method. Cost-wise, rate journal is cheaper as compared to isopynic. Instrument-wise, rate journal, so we have a lot of robust cheap quality instrument available, whereas in case of isopynic, we need to have a improved and advanced centrifuge instrument to be used for the isopynic separation. So these are some of the differences between the rate journal and isopynic, and this is a very important topic you should know. So coming on to the another part, that is analytical ultracentrifugation. This is also denoted as AUC, analytical ultracentrifugation. And if you recall, in my first slide when I was telling Swedberg, so Swedberg has been credited for the discovery of ultracentrifugation also. Ultra means very high speed centrifugation. So that's why the term has been coined ultracentrifugation, and Swedberg has been credited for the discovery. So if you see some of the points which I have listed here, so analytical ultracentrifugation, so it imposed very high centrifugal force on suspended particles, and many a times because of its high speed, there is a need to create a vacuum inside the chamber. Because if vacuum is not there, there is every possibility that it will catch fire because of its high speed and the friction which is imposed by the area. So this ultracentrifugation are basically vacuum-based area is there where we are going to have a specialized rotor to be used to create or impose a high centrifugal force on the suspended particles. It can run, if you see, it can run at about 1,20,000 to 1,50,000 RPM, and RCF may be more than 6 lakh G. So that much value we can impose using ultracentrifugation. But then, in order to impose such high centrifugal force or such high RPM or RCF, there is a certain prerequisite, as one I told earlier, that the chamber should be vacuumed. Another is that the rotor which you are going to use, that should be tensile enough to exert such forces, because this speed is very high. The load point which you are going to use to put the rotor, that should be specialized one to tolerate such high speed. Then there should be different sensors to calibrate the temperature, to analyze the imbalance of motors, because imbalance of motor is one of the biggest problem in creating such a high centrifugal force or such a high centrifugal speed. Because if your rotor is not balanced, so there is every possibility that it will break the node point, and if it breaks the node point, it will just come out bursting from the chamber. So this is one of the common accident which happens. So that's why all these ultracentrifuges have a automatic imbalance sensors which will tell you that there is a problem in the sample or the centrifugation tube which you have used along with the sample, and unless it is balanced, it will not allow the ultracentrifugation to run. So there is a temperature sensor which will tell you what is the temperature inside and how it should be regulated. There is a scattering light sensor which will check the change in the light or the reflectile of the sample which you are going to use. So these are different sensors which are which comes with the instrument, and this is prerequisite before using the ultracentrifugation. Regarding separation, you can separate a particle as less as 10 micron, as I have written here, and the volume. So as we are doing in our lab, from 0.2 to 5.5 ml, that much volume you can use in ultracentrifugation, and then you can separate the particle with very high purity. So especially as I told in earlier slide, so ultracentrifugation is basically used for the separation of organelles, Many times you have heard separation of chloroplast or mitochondria or separation of nucleic acid, especially DNA or RNA. So we are using this ultracentrifugation, and the material which you are going to get out of this ultracentrifugation is of very high and pure, very high quality, and is pure. So that was one classification based on the sample volume and the speed which we are going to use. So there is another classification of centrifugation which is basically based on the instrument which you are going to use. So based on the instrument, I think in your lab, many of you have seen different types of centrifugation. So we have a tabletop, we have a spin wheel, we have a floor model, we have a high speed, we have a refrigerated, we have a flanging, we have a slant centrifuge, we have a ultra centrifuge, etc. So based on the instrument, so centrifugation has been further classified into 5 different types. So I have listed here. The first type is called as small bench centrifugation. So as I told, based on the instrument means based on the RPM and the RCF which instrument is going to provide, it has been classified into different types. And whatever instrument we are using all over the world, so all those types fit into these 5 types. So the first is the small bench centrifugation, where the RPM speed is 4,000 to 6,000 RPM and RCF is 3,000 to 7,000 G. So this is small bench type of centrifugation is basically used for like sedimentation of blood samples or maybe for small spin wheel based work. So in that case, we are using small bench centrifugation. There is another type which is called as large capacity refrigerated centrifuge. So refrigerated means there is a facility for the refrigeration and easily you can maintain the temperature inside the centrifugation chamber. And large capacity means it has a RPM of 6,000 and it has a G value or RCF of 6,000 G. And large capacity refrigerated centrifuge is basically used to collect samples like RBC, yeast cells, and some of the other microorganism based work which we are doing in our lab. So in all those cases, we are using a large capacity refrigerated centrifuge. There is a third classification which is called as high speed refrigerated centrifuge. High speed refrigerated means it has a RPM of 25,000 and it has a RCF of 60,000 G. So RPM is 25,000 and RCF is 60,000 G. So it is basically preferred to be used in case of collecting microorganisms, organelles, plasmid isolation, most of the molecular biology based work which we are doing in our lab. In all those cases, we are using high speed refrigerated centrifuge, even for the extraction of protein, even for proteomic characterization. So in all those cases, most of the routine work which we are doing in our lab for molecular biology and for proteomics, so we prefer to use high speed refrigerated centrifuge having a RPM up to 25,000 RPM and RCF of 60,000 G. Then there is another classification, that is ultracentrifuge. So ultracentrifuge, maybe in subsequent slide, I'll tell you we have further 2 different classifications of ultracentrifuge. One is preparative ultracentrifuge and another is analytical ultracentrifuge. So differences that I'll show you in the next slide. Let me repeat once. I told ultracentrifuge has been further classified into 2 different types. One is preparative ultracentrifuge and another is analytical ultracentrifuge. And the last classification is continuous flow classification, and this is continuous flow centrifugation, and this is basically used in industry. So industry people, they are using a mega centrifuge or big centrifuge for the separation of these particles, even for this effluent, this waste removal and then purification of effluent. So in that case also they are using continuous flow centrifuge, mega centrifuge with a facility to remove the particles or the waste product which is present in the sample because of centrifugal force. So continuous flow is basically used in industry and for this purification based purpose. So these are 5 different classifications of centrifugation based on the instrument, based on the RPM and the RCF of the instrument which they are going to provide. Now coming on to ultracentrifugation, as I told that in subsequent slide I'll tell you, and even I had already given you information that this ultracentrifugation by default was first discovered by Swedish biochemist Swedborg. So he first discovered ultracentrifugation to separate different colloid particle or salts, and he was also awarded Nobel Prize in Chemistry in 1926 for his research on colloid particles and protein using the ultracentrifuge. So this gentleman has been credited for the discovery of ultracentrifugation with different facilities. Of course, that doesn't match with the ultracentrifuge which we have today, but then he is credited with the discovery of ultracentrifugation. If you see the ultracentrifugation, so I have just shown one figure here. So this is ultracentrifuge of Beckman. Beckman is a multinational company which used to make this ultracentrifuge. This is a specialized technique used to spin samples at exceptionally high speed. As the term suggests, ultra means very high speed, and then centrifugation. So current ultracentrifuges which we have, so it can create up to 1,50,000 RPM, which is equivalent to almost 10 lakh G. So exceptionally high speed is one of the prerequisites to be called as ultracentrifuge. And if you see the bottom figure, so this is the workflow for the ultracentrifuge. If you see here some of the things which has been written here, like if you see the motor and the rotor which is kept at the top of this, there is an armored chamber. Armored chamber means even if some mishappening happens, so at such a high speed, this rotor should not come out of this chamber. That's why this is armored chamber. Then you have a vacuum pump. Vacuum pump means it is going to first create vacuum inside the chamber. Once vacuum is created, then only it will allow this motor to run. Then you have a cooling facility here. So there is a sensors which will detect the temperature inside the chamber, and then many a times the temperature which we fix, so immediately it will maintain that particular temperature. Then we have a small detector also, so which will detect the centrifuge of your particle on actual basis. So these are some of the facilities, common facilities linked with ultracentrifuge in order to achieve such a exceptionally high speed. Regarding applications, as I told earlier, so most of the common application which we are doing here at Agriculture Institute is separation or the isolation of nucleic acid, especially high quality DNA and RNA. We are using this method. So other than this, even for separation of organelles also, especially chloroplasts, so people they are using ultracentrifuge. Other than this, you can also use it for the separation of small particles such as viruses, viral particles, protein or complexes, lipoprotein, even a plasmid DNA. So all these things easily you can separate using the ultracentrifugation. The only problem with ultracentrifugation is that a lot of setup is required before using this ultracentrifuge. Means once you have taken sample in your centrifuge tube, first you have to measure or you have to weigh all those centrifuge tubes that it should have equal weight. Even if there is a fluctuation of few grams, so when you feed your sample into the ultracentrifuge, the centrifuge will not switch on. It will say there is a imbalance in the centrifuge tube. Even the rotor which you are going to use, if there is slight fluctuation in the pin or the nodal where you are going to put your rotor, so the instrument will not run. Even like this, all the sensors, they should work perfectly, and these are the prerequisites. Even if there is error in one or the other sensor, so ultracentrifuge will not operate. So these are some of the automated features associated with ultracentrifuge, which makes it little bit complex for use. But then still people they are using to get high quality material. Regarding classifications, as I told earlier, this is an important one, that ultracentrifugation has further been classified into two different types. One is called as analytical ultracentrifugation and other is called as preparative ultracentrifugation. And if you see the classifications, so in case of analytical ultracentrifugation, the RPM which we can achieve is 70,000 RPM, whereas in case of preparative ultracentrifugation, it is the 80,000 RPM on which we are going to separate the particles. In case of analytical ultracentrifugation, we can achieve up to 5 lakh G, which is the RCF value, whereas in case of preparative ultracentrifugation, we can achieve up to 6 lakh G. In case of analytical ultracentrifugation, so we have optical sensors which analyze the changes in the particle which you are going to use for the separation using the ultracentrifugation. Whereas in case of preparative ultracentrifugation, we have different type of sensors, like we have infrared temperature sensors, we have imbalance rotor sensors, we have a scattering Rayleigh we have a scattering plate sensors. So different types of sensors are installed in preparative ultracentrifugation. In case of analytical ultracentrifugation, we have a small Rayleigh-based system for the visual observation, whereas in case of preparative, as I told earlier, so they have different type of sensors to analyze the temperature, rotor imbalance, the changes in the sample, and other parameters or variables linked with this. So these are some of the critical differences between the analytical ultracentrifugation and preparative ultracentrifugation. So if somebody asks you, so how you are going to classify the ultracentrifugation? So basically we are going to classify it based on the RPM or the RCF and based on the facilities linked with these instruments. So we have analytical and we have preparative ultracentrifugation. These are the RPM and RCF associated with these two different types of ultracentrifugation. Now coming on to another important component of centrifugation, that is called as the rotor. So you cannot think of centrifugation without rotor. So rotor plays a very important role in centrifugation. So as you have a motor in your instrument, so is the rotor, which is the detachable component of centrifuge, and easily you can detach rotor out of the instrument. So rotor, we have 5 different types of rotor available for centrifugation. So we have 5 different types of rotor available for centrifugation. One is called, first is fixed angle rotor. Then we have a swinging bucket rotor. Fixed angle rotor means most of the time the centrifugation machine which we are using in our lab is fixed angle rotor, means it is fixed, sit at the nozzle, and then you can centrifuge. You cannot change the angle of the rotor which you are going to use. Whereas we have another type which is called as swinging bucket rotor. So swinging bucket rotor means there is an arm attached with the socket, and when you centrifuge, so that arm will open, and once it opens, so it will take a specific angle, and on this specific angle, most of the time it is between 17 to 45 degrees Celsius. It takes a specific angle, and that this specific angle it will go on rotating. So that is called as swinging bucket rotor. Then we have a third type of rotor which is called as vertical rotor, means rotor will be something like this and it will go on rotating in this way. So that is a vertical rotor. Then where the angle is mostly 0 degrees. Then we have another which is called as near vertical rotor, means there will be little bit of slanting in the rotor, and that we are using for the centrifugation. And then we have a continuous flow rotor, as I told, used by the industry people, where continuously samples or the outcome of the centrifuge will be removed from that, and then continuously that rotor will go on working. It is a mega one, that is continuous flow rotor. So let me repeat once. I told, so whatever rotor we are going to use, based on the angle of orientation, it has been classified into 5 different types. So we have a fixed angle rotor, we have a swinging bucket rotor, we have a vertical rotor, we have a near vertical rotor, and then we have a continuous flow rotor. Now, this rotor further has been classified based on the type of material which is going to be used to make these rotors. So based on the material which you are going to use to make these rotors, it has been classified into two different types. So first type where we are going to use brass or steel or perspex. So this is one type which is basically lighter, having very high tensile strength and can sustain a very high RPM or RCF also. There is another classification where we are using aluminum or titanium or alloy based rotors. So now most of the centrifuges which we are coming, so they have a rotor made of alloy. The advantage is that it will be a lighter, it will have a very high tensile strength and durability is very high. So whatever rotor we are going to use nowadays has been broadly classified into two different types based on the material which you are going to use. One is where we are going to use the brass or the steel or the perspex. So these will have a very high tensile strength, but then these rotors have a weight, and then its durability is little bit compromised. Whereas in case of motor made up of aluminum or titanium or alloy based rotors, so they have very high tensile strength also, they have very high durability also, cost is also high, and then they are lighter weight. Easily anybody can lift, because this is also one of the major problems when you are working in your lab and every time you have to remove your rotor, every time you have to put your rotor. So few times it's okay, but then every time when you have to weigh some 3-4 kg or 5 kg or 6 kg rotor or maybe more than that, so it becomes difficult. So for that purpose, and these alloy based rotors, they are very lighter weight, high tensile strength, high durability. So these are some of the classifications. Then this rotor has also been classified based on the design. So based on the design, these rotors has been classified into again 4 different types. So the first type is swinging bucket rotor. Swinging bucket, as I told earlier, so there will be an arm, and when you centrifuge, because of centrifugal force, this arm will open, and once arm will open, so at that speed only it will go on centrifuging, and then there will be, if you see here, I have written that the particle which you are going to centrifuge in case of swinging bucket will accumulate at the bottom or most of the time at the wall of the centrifuge tube which you are going to use. So in case of swinging bucket, accumulation is at the base or the bottom of the tube or at the wall of the tube. The another classification is fixed angle classification or fixed angle rotor. Fixed angle where the angle of the rotor has been fixed to 14 to 40 degrees. This varies from 14 to 40 degrees. This is fixed, and here pellet accumulate at outermost point of the tube. So based on the angle, so when you centrifuge at high speed, the pellet will accumulate at the outermost point, the farthest point of that particular centrifuge tube. So your pellet will go and accumulate over there. Why we have different types of these rotors? Maybe because of a specific use. For example, swinging bucket. So most of the time for pigment isolation, so we prefer to use a swinging bucket. So in case of fixed angle, so most of the time these microorganism based separation, so we prefer to use fixed angle. So all these different types are based on different uses. We have a third classification which is called as vertical tube classification or vertical tube centrifugation. Vertical tube means tube will be in a vertical position. The angle is 0 degree, and sedimentation is in case of vertical tube is the fastest or quickest one as compared to others. Maybe because of the length or the side wall is very near to the center of the gravity. Maybe because of this. So sedimentation in case of vertical tube is the quickest one, and once you start centrifuging, easily all your particle will sediment on the wall of the centrifuge tube. So entire wall will have a particle sedimented on the surface. So vertical tube This is an important point that sedimentation is quickest in case of vertical tube. And then we have another classification which is called as zonal centrifugation. So in case of zonal centrifugation, so batch centrifugation is basically carried out. And as I told again, this zonal centrifugation or the batch centrifugation is basically taken care of by industry people or some of the waste treatment plants. So they are also using zonal centrifugation for the separation of the unwanted particle or waste material present in the solution. So that they use to remove through zonal or the continuous flow based method, and then the purification is carried out. So to repeat, I told rotor is one of the very important and detachable component of centrifugation, and this rotor has been classified into different types. One classification is based on the material which you are going to use to make the rotor. It has been classified into two different types. One is made up of brass or steel or perspex glass. So these type of rotors have very high tensile strength, but it has a weight, and then even durability is not much. Whereas we have another classification where you are going to use aluminum or titanium or alloy based rotor, which has very high durability, high tensile strength, weight is lighter, but cost is high, and nowadays it is preferred one. Then again, I told that this rotor has been classified based on the design which you are going to use into four different types. One is swinging bucket rotor, one is swinging bucket rotor, where when you centrifuge, so your particle is going to accumulate at the bottom of the tube. Then another is fixed angle, where a specific angle is fixed, that is 14 to 40 degrees Celsius for the centrifuge tube. And once you separate or once you centrifuge, your particle will sit at the farthest point of the centrifuge tube. Third is a vertical tube, where the angle is 0 degree, where the angle is 0 degree, and I told this is one of the quickest method, or the sedimentation is the quickest one as compared to other different type of method, and the particle is pelleted all over the wall. And the last one is zonal centrifugation or batch centrifugation, which is basically used by the industry people and the purification plants. So water purification plants, so people, they are using there for a continuous flow and centrifugation to remove the waste particle out of the water. So these are four classifications based on the design. Coming on to the parts of a centrifuge. So there are, this we should know, we have a core part which is basically a rotor. So rotor that I have explained you. Then we have a arm or a radiating arm which is fixed at a certain angle. Then you have a hollow tube attached for the sample replacement. Then you have a ball bearing for the centrifugation of that particular rotor. Then you have a drum. Then you have a drum which is basically a aluminum or titanium grade drum. Then you have a controlling knob. Then you have a motor and brake assembly. Means suppose if some emergency happens, so you have a automated brake assembly or brake shoes which you can press and immediately you can stop the centrifuge. Then you have a cover. Cover means when you put your sample, then easily you can knob using the cover at the top. Then you have a blade to close that particular sample lot. Then you have a basket in which you are going to fit your sample, and then you have a latch arms and then motors and other things. Let me tell you that these parts of centrifuge varies with the type, design, company, speed, RPM, RCF, different factors are there, and all these parts varies with the type of instrument, type of company we are going to purchase. So it's not hard and fast rule that if I have written all these things, it should be present in all the motors. But then by thumb rule, there are few things which is basic one and which must be present in any of the centrifuge. That is the rotor, which is must, motor, which provides that much speed to the rotor, then one chamber, so that should be specialized chamber, then one bucket that will take care, or that will close, or that will stop the flickering or the flicking of the sample from your tube. And then you should have some of the PCBs which can control the speed which can, in case of emergency, which can immediately stop. So all those things, display board, that should be there. So these are some of the common things which should be present in your centrifuge machine for the operation. So this was in brief about the centrifugation process. I think I'll stop here, and maybe next class will be the last